I'm trying to find the cell potential for a particular reaction. I can measure it experimentally using a voltmeter, and let's take a look at the particular cell that's shown here, where I have zinc reacting with acid, so I have 2 hydrogen ions, and it goes to zinc ions and hydrogen gas. This may be a reaction that you've done in your first year chemistry class. If I use a voltmeter, what I'll find is that it measures a cell potential of 0.76 volts for this reaction. So if I were to write out the cell potential reaction, it looks something like this. So the E0 for my cell equals the E0 for hydrogen, going from hydrogen ions to H2, plus the E0 for zinc, going to zinc plus 2. So I have hydrogen reducing, I have zinc oxidizing. So I have one oxidation reaction, one reduction reaction in the same container. And we learned in the last vodcast that E0 for hydrogen is 0. And from our standard reduction potentials chart, zinc is oxidizing. That doesn't help us. So we have to find that reaction and then look at what happens when we reduce it. So for zinc, on our reduction potentials chart, that's what we'll find is zinc plus 2 to zinc, and we will find a negative 0.76 volts. Since we are flipping the reaction from reduction to oxidation, we change the sign of E0. So now if I add these two together, I have 0 plus 0.76, and so the E0 for my cell, being the sum of my oxidation and reduction potentials, is 0.76 volts. For standard reduction potentials, that's what the 0 means. Same as for delta G0, delta H0, it's standard conditions. So standard conditions when I'm dealing with electrochemical cells are going to be 1 molar solutions. If I'm dealing with gases, the pressure is going to be 1 atmosphere. Let's take a look at another reaction. Here we have a reaction between zinc and copper. So we have zinc on one side of our galvanic cell. We have zinc ion solutions, and we have zinc metal as our electrode. In our other solution, we have copper as our electrode. We have copper ions in solution. We're dealing with standard conditions because we have zinc ions as a 1 molar solution. We have copper ions as a 1 molar solution, so we're in standard conditions, so we have E0. So the E0 for my cell is going to be the half cell for zinc plus the half cell for copper. My reaction shows zinc metal and copper ions as reactants, zinc ions and copper metal as products. So that's how I have it written. If I look at the reduction potentials for zinc, we saw before it is negative 0.76. Reduction potential is positive 0.34. When we're looking at our two reduction potentials on that reduction potentials chart, how do we tell which of the metals is supposed to oxidize, which of the metals is supposed to reduce? Well, we look at which is more positive. Copper is more positive. It stays as a reduction potential. Because zinc is more negative, it's going to flip, and it becomes the species that oxidizes. So again, the more positive E0 stays as written, stays as a reduction potential. The more negative E0 gets flipped, you change the sign, and it becomes an oxidation reaction. So if I take these numbers now, I have for zinc, instead of a negative 0.76, I have a positive 0.76. For copper, I have a positive 0.34. I add them together and I get my E0 of 1.10 volts for the E0 for the cell. There's a table of E0s in your book on page 833. There's also one of the 4 pages of your green sheets is a reduction potentials chart. What these two circles here show us is zinc is oxidizing. So this zinc atom gave its electrons up. The electrons are passing through the wire, and it forms this zinc ion. So these are holes where zinc atoms were. They've given up their electrons and have become zinc ions in solution. On the copper side, we have electrons coming in from the zinc side. So the electrons hang out here and it attracts this copper atom, so we create a neutral copper atom that we've stuck onto our electrode. So this is probably the original surface of our electrode, and the copper atoms that are outside of it are ones that have been added on thanks to this electrochemical process. Okay, so what happens when one reaction needs to be multiplied to balance things out? So here I'm looking at iron plus 3 and copper. So I go to iron plus 2 and copper plus 2. Well, if I want to add those together, my half reaction is iron plus 3 goes to iron plus 2. It involves 1 electron. For copper, I have copper going to copper plus 2. It involves 2 electrons. So to be able to add these, I have to multiply my iron half reaction by 2. What I do with my E0s for the half reaction is I simply add them. I don't multiply by coefficients. E0s are intensive properties. They don't depend on quantity. An intensive property that you're familiar with or more familiar with would be density, and intensive properties don't depend on quantity. Again, let's see if we can figure out which way where my reaction is going to run. I have a silver metal electrode, silver ion solution, and a copper metal, copper ion solution. The reduction potential of each is given, so I have silver at 0.8 volts. I have copper at 0.34 volts. Which one is going to stay as a reduction potential? Hopefully you remembered that the larger one stays as a reduction potential, so silver is going to reduce from +1 to 0. Copper then is going to flip and oxidize. We want to end up with an E0 that's positive, because that means that the galvanic cell is going to run of its own accord. It's spontaneous. So we're going to have silver reducing, copper's going to oxidize, so we take the E0s of 0.8 for silver, make copper a negative 0.34, and we get an E0 of 0.46 for our galvanic cell that uses those two metals. Okay, some background, bit of definitions. We don't have time to really derive these equations, so you just kind of have to work through this with me. If you want more background or want to take it through more slowly, you can read through sections 17.3 and 17.4. We're just going to kind of cruise through this. Starting out with the definition of work. Work is a transfer of energy or a change in energy. And we're going to symbolize it by delta E, E for energy. If we have an ideal system or an ideal process, we lose no energy. So work is equal to Q, which is charge, times cell potential. So we can put that together, and here's our equation. The maximum amount of work that an electrochemical cell can do is equal to the charge times the maximum cell potential. Work done by the cell is negative. If work is done on the cell, it's positive. And my maximum cell potential is positive. That means it's spontaneous. So if I'm going to write it more accurately, I'm going to write it as negative work is equal to Q times E max. In reality, we never reach maximum work because energy is always dissipated. We've learned in chemistry that reactions very rarely go to 100% completion. We always have some reactants hanging around. So we're never going to get our maximum E0, means we're never going to reach our maximum work. Again, Q is charge, and the charge for 1 mole of electrons is called 1 Faraday. And 1 Faraday equals 96,485 coulombs. So Coulomb is the unit of charge. The charge on 1 electron is 1.6 negative, because it's an electron, 1.6 times 10 to the negative 19 coulombs. It's a very small charge. So I don't deal in charges of electrons. Generally, I deal in charges of a mole of electrons. So Avogadro's number times the charge for 1 electron gives me a Faraday, or 96,485 coulombs per 1 mole. So for reaction, the charge equals the number of moles, remember that's N, times the Faraday, which is charge per mole. Well, that kind of makes sense, hopefully. And maximum work equals delta G. Remember, delta G equals free energy, which is the energy available to do work. Thought you were done with all this tying together stuff, huh? So now I can put it all together. My maximum work equals Q times E max equals delta G. All right, now I'm going to put it all together and link this all together. So here I'm substituting N times F in for Q, so Q times E max equals delta G. So I've got NFE equals delta G. But remember, back in my original equation, I had work as negative. So I don't want to forget about that. So I'm going to bring that down now. So I have negative work equals Q times E max. So here's my Q, E max equals negative work equals delta G0. So now we have an equation that relates number of moles of electrons, the charge of a mole of electrons, our cell potential with delta G. So this is an equation that we'll be working with when we're doing some calculations and relating it to free energy for this particular chapter. All right, so now let's put it to good use. Let's calculate the delta G0 for the reaction, and we have copper plus 2 reacting with iron metal, and we get copper metal and iron plus 2. So how do we start that out? First thing I want to do is write the two half-cell reactions. So I have copper ions reducing to copper metal. Half-cell reaction for that is 0.34 volts. We've already seen this number before. Iron, going from iron plus 2 to iron, the reduction half-cell potential for that is going to be negative 0.44 volts. So we've already seen that we're going to have to flip the iron. So we're going to make that go in that reaction, and we're going to make that then a positive 0.44 volt. And then if I add them together, I get E for the cell is 0.34 for the copper, positive 0.44 for the iron, and I get 0.78 volts for my cell. Now, from the equation we just learned, we have delta G0 equals negative NFE. Well, how many moles of electrons are being transferred? If I look at the reaction, I have 2 moles of electrons, so negative 2. A Faraday is 96,485, and my E0 is 0.78. So if I do the math, I end up with a delta G of negative 1.5 times 10 to the 5th. And this is in joules. All right, the next part of the reaction is this spontaneous. Well, I look at delta G, I've got a negative delta G, so the answer is yes. And why? Justification, delta G is negative.